Okay, thank you, Sid, for introducing me. I am Rungployphan, and I'm going to share with you about what motivates me to study my PhD and a bit of what I have found so far. So now I'm a final year PhD student here, and this talk is about the solar wind interaction with the Earth magnetosphere using multi-spacecraft observations. So what led me to study this topic? So it was some 5 years ago when I was still an undergrad. I had an opportunity to volunteer in a conference. It was a conference about space weather. And at the time I was in Thailand. I was studying physics in Thailand. And the conference was in Bangkok. So as a volunteer, I got to choose what session I wanted to be in. And I attended a session about geomagnetic substorm, which I will show you in a minute. So at the conference, I learned that, okay, the Earth, our planet, we got very lucky because the space is not empty, and we got energetic particles coming from the sun, coming from far away, and they are constantly bombarding the Earth. But the Earth has the magnetic field that shields us from the space radiation, and that's why lives on Earth can survive and evolve. And we are here now as humans to think about what's it happening outside the space, which is very cool. So, the shield of the Earth's magnetic field is not perfect. There can still be some particles that can come into the Earth's atmosphere. And how do we know? We know it because we see aurora, or northern lights or southern lights. But so they are beautiful, but there can be some danger as well, because there can be strong space weather events, such as coronal mass ejection, that can harm our space technology. And these days, the space weather become increasingly important because we have space technology, such as satellites, GPS, and we are increasingly rely on this technology. And we are worried if we won't have internet one day, for example. And this space radiation can harm the airline passengers and also astronaut safety. I will show you more about the strong space weather event afterwards. But so coming back from the conference, I was very motivated to learn about plasma physics, to learn how can we protect the planet. So there is this plasma process called magnetic reconnection, which allows the magnetic energy that is stored in the field to be plasma, acceleration, and kinetic energy. So we can think about a slingshot that releases its energy. And this process can happen on the day side of the Earth. So there was a British scientist in 1961, Jim Dang-jae. He proposed that the magnetic reconnection can occur on the day side because, okay, the Earth's magnetic field is pointing northward, right? And if the solar wind has the magnetic field that points southward, it can reconnect on the day side. And over there, reconnection can occur. And reconnection can occur also at the sun. There can be a bunch of magnetic fields emerging from the sun's surface and get extended and squashed in the middle. So this video will show you the process called geomagnetic substorm that is triggered by magnetic reconnection. So the sun is a big plasma ball. I will explain you in the next slide what is plasma. And the sun is energetic, and it sends solar wind coming to the Earth magnetosphere. And the magnetosphere can open on the day side because of reconnection. And then magnetic fields can pile up on the night side, and they can get squashed. And the reconnection can occur there as well. And there, the magnetic field releases its energy towards the polar regions, and that's why we see the aurora. Okay, next slide. Oh no. Okay, so plasma physics. So when I came back at my uni, I was very inspired to study plasma physics. So plasma is the hot gas that is ionized into ions and electrons. There is the fourth state of matter. Plasma can be found at lightning or neon lights or a plasma ball. And the plasmas, since they are ions and electrons, they are described, they behave following electric field and magnetic field. And also, since they are particles, they have mass, right? So they behave following Newton's second law, but the force is the electromagnetic force. So to study plasma physics, you have to solve analytically using pen and paper, following particles, and these particles behave following electric field and magnetic field. But it's very hard to do that. So in my senior project as an undergrad, I used a particle in cell simulation to track particles using these equations. But it's very hard. I mean, it will be very computationally expensive. If you use a normal computer, you might take like 3 months to calculate this because there are billions of particles. But I used a supercomputer, so it finished in 12 hours. But there is a simpler way to do it. If you consider a very large scale, you can estimate them as fluids. So you don't have to use lots of computational time. So in 2015, when I was in my fourth year, there was this space mission from NASA called magnetospheric multiscale. So this mission, a nickname MMS, was aimed to study magnetic reconnection using the Earth magnetosphere as a laboratory. So I was very motivated to see if my simulation study is true, using this mission to confirm my result. So in that year, I came to Exeter University because there is a lecturer, there is a researcher that is specialized in space plasma observations. And so Dr. Claire Fulong is specialized in observations, and she works with some cluster mission. So cluster mission is a European agency mission, and it was launched in 2000. But this mission is actually the second mission. I mean, so there was cluster mission in 1995 that was launched, but then the rocket exploded and we lost all of the satellites. So this mission was rebuilt again and it was launched in 2000. And there was MMS mission that was launched in 2015. But these two missions are the 4 spacecraft missions. So they're basically 4 satellites, 4 identical satellites, forming tetrahedron configuration, and they co-fly in space. So I wanted to study the Earth magnetopause, and the Earth magnetopause is quite complex. It's the magnetospheric boundary that is formed, and it separates the magnetic field of the Earth from the solar wind. So you can think of it like if there's a stone or a pole in the middle of a river, and it just forms a boundary that is separate. So, but the Earth magnetospheric boundary can undulate like surface waves in ocean, but we can't see them like surface waves in ocean. So my research wanted to use the cluster mission to see these waves in space. So the surface waves is called Kelvin-Helmholtz waves, and is triggered by KH instability. And the Earth flank magnetopause can be subject to this instability. And this instability can facilitate solar wind entries because they can trigger magnetic reconnection inside. And I want to use this spacecraft to see the complex structures of these waves. So now you may wonder why it has to be tetrahedron configuration. So a typical spacecraft observation would look like this. It's just up and down. It has no sense. And you just have to use the best of your knowledge to guess. But so the main problem was, how do we tell if it's fluctuation in space or time? So you can use 2 satellites and see how the wave propagates. But we have to hope our best to hope that the spacecraft will be in a likely configuration. But the best way is to send 4 probes, and there we can resolve the space and time ambiguity. And also, since we use Maxwell equations a lot in plasma physics, so the delta, the triangle, is basically the gradient. And we want to solve the gradient in 3 dimensions. So I choose the 4 spacecraft techniques to study these waves. The first technique is the magnetic curvature to tell how curved the magnetic field is. And also, since it has the vertical shape, I want to quantify this vorticity. So I set up my simulation and capture the wave along the Earth flank magnetopause. And I also use some varying tetrahedron size because there are 2 missions, cluster and MMS. So the MMS has a very small tetrahedron formation, and cluster has a very large one. And using the simulation, I produced the signatures, what the waves would look like in space. So I have a virtual spacecraft flying. And I resolve the patterns of the curvature using the cluster scale size. The middle one is the cluster direction to tell how twist is the waves, and also the vorticity. And if I use the MMS mission, I get slightly different signatures. So in space, now I use cluster observations to tell if I see anything that resembles my simulation. And I confirm, my research confirmed the signatures that I predicted in the simulation. And I can use there can be other applications of the 4 spacecraft technique as well. For example, this one is the observation of a flux rope. In the past, if we have just 1 spacecraft, the best we can do is just to fit the data into a sinusoidal model, for example. But here, using 4 spacecraft, I can resolve the internal structure of the waves and can say, okay, this pattern is the cross-section of a cross-section. Is the cross-section of a flux rope, sorry. Okay, what's next? So the scientific community is hoping to have a simultaneous observation of 4 spacecraft tetrahedron in 2 scales, so we can resolve variations of complex magnetic structures. Because now, using 1 mission, we can resolve just 1 scale at a time. And there was a proposal about cross-scale vision. So they proposed to send satellites forming tetrahedron configuration in 3 scales. So in this way, we can resolve the fluid and ion and electron scales at the same time. How much time do you have left?
You've got 6 minutes.
Okay, cool. So space weather. So I want to talk more about space weather. And space weather, first I want to introduce you some terms. So coronal mass ejections are the large-scale magnetic bubbles expanding out from the sun. And they cause geomagnetic substorms, aurora, and more. Solar flare is a sudden flash of the sun surface. And the solar energetic particles are the high energy particles coming from the sun. And the geomagnetic storm are bigger than geomagnetic substorm. So the geomagnetic storm is caused by the CME, and geomagnetic substorm is just caused by solar wind. So I want to introduce you some extreme space weather events. For example, in 1859, this event was recorded by British astronomers Richard Carrington and Richard Hodgson. So it was a powerful geomagnetic storm that hits directly into the Earth's magnetosphere. If it happens today, it would cause blackout for like 16 to 1 to 2 years, and it will affect 20 to 40 million people on Earth. And the economic cost would be like up to $2.6 trillion. And there was a geomagnetic storm in 1989. And this storm caused the, so in 1859, we didn't have much space technology. So at the time, only telegraph poles were damaged. But in 1989, we had some power grid already. So this storm caused the outage for 9 hours in Canada, and the aurora could be seen as far as south as Texas and Florida in the US. And at the time, it was like the end of the Cold War. So people were worried if Russia sent out a missile, but it was actually a space weather event. And in 2012, there was a solar storm, but our planet got very lucky again because it passed the Earth orbit. So I will show you the video. Okay, so this is the coronal mass ejection. And it expands out from the sun. Here you see the Earth, the yellow dot. And here you see the CME expanding out towards stereo A. Stereo A is one of our satellites, but the Earth is on the other side. So if this event happened 9 days earlier, it will hit the Earth, and these days we might be still fixing our satellites. And there was one last event that I want to introduce. So there was a solar flare last year during storm Hurricane Irma. So it was an unlucky coincidence of space and Earth weather. So at the time on September 6th, there was some Hurricane Irma passing the Caribbean islands, and there were lots of damage. And people were trying to help people in the Caribbean. And on that day, in the morning, there was a solar flare, and solar flare disrupted our radio emission. So at the time, when people were trying to help with the damage that the hurricane causes, people couldn't use the radio to communicate. So it happened when we need our technology the most. So it's one example of space weather event. Okay. And some of you might wonder if space weather can impact the climate on Earth. Well, solar irradiance is one of the causes, but there are other causes such as some greenhouse gas, volcanoes, or El Niño, La Niña. And this is the Earth's surface temperature. And you can see that the greenhouse is the main cause of the temperature on Earth. So it's not the sun's fault. So to summarize, Sun-Earth interaction is important to study space weather that can have wide socio-economic impact. And many satellites are probing the Sun-Earth interaction, and these will lead to a better understanding of space weather. And using 4 spacecraft missions, you can resolve complex structures of plasma in space that can contribute to Sun-Earth interaction understanding and also space weather understanding. If you want to learn more, you can look up Metophy's space weather team. We have a dedicated team to study space weather. And you can, if you're curious about my research, you can look for this paper and there will be more articles to be published. So thank you for your attention.